Everybody, welcome to Albert Chua's Master of Applied Science thesis oral presentation. His thesis title is going to be Exploring Deep Learning and Hybrid Controllers for Connected Autonomous Vehicles Networks under Large or Time-Varying Delays. So Albert, you will have about 20 to 25 minutes of oral presentation time. And I'm going to give you some hints if you're going over time. And then we will follow up with questions and answers from the committee members. Please go ahead.
Okay, sounds good. So I'm gonna go ahead and just share my screen. Can everyone see the presentation just fine?
Yes.
Okay. Alright, so thank you everyone for coming. I see there is, well, my entire committee, which was put together in quite a rush, so thank you so much for helping me out. And I also see some community members as well as family, so thank you for coming out to support me. Without further ado, we'll get started. I'd like to start off with a look at the big picture technology that our thesis is going to be contributing to. Intelligent transportation systems offer solutions for adaptive, faster, and more capable transportation. In the modern day, ITS systems are envisioned to connect vehicles to infrastructure by providing real-time congestion information that might influence the behavior of traffic signals or toll route pricing. ITS may also connect pedestrians with vehicles for proximity warning. There is a particular interest in vehicle-vehicle connections, so vehicle-to-vehicle connections, and these are also known as connected vehicle networks. Additionally, these vehicles may be autonomous and fully controllable by algorithm, which then we call them the connected autonomous vehicle networks. These networks can benefit ITS environment by eliminating the need for vehicles to slow down during lane merges and by increasing traffic density and the average velocity in so-called CACC scenarios. CACC CACC stands for Cooperative Adaptive Cruise Control. And actually, a less obvious benefit of CACC systems are that they are able to dampen disturbances such as emergency braking. In the animation here, you can see when the red cars perform some dangerous maneuvers, the vehicles behind it have to emergency brake. And these disturbances in traffic has been shown to cause phantom traffic jams. And phantom because when you drive up to the cause of the traffic jam, you really don't see anything, and I'm sure a lot of us have experienced this. For the above reasons, there's a great deal of interest in CACC research. This thesis is our group's initial effort on the CACC topic. When we surveyed the literature, we found that it was very popular to consider a fully connected, forward-looking topology. This means that between every vehicle pair where I is less than j, there will be a communication link. In literature, a big challenge in CACC lies in mitigating the time delays that will inevitably be a part of wireless communication technology. Most studies use constant time delays of 100 milliseconds to 300 milliseconds to approximate the random time varying delays of wireless systems, because in the modeling of CACC systems, time varying delays are create very highly nonlinear systems and are difficult to analyze. We want to know if it is appropriate in general to use these constant time delay approximations to approximate time varying ones. And also, what would happen if the delays were to be increased to 1 second or even 5 seconds. This is an overview of our entire thesis journey. Our thesis contributions are shown in the green color, and ultimately they were the fruits of our effort in trying to answer our guiding questions. We actually end up refining one of our research questions as we learned more about the CACC systems, and it led us to propose a new method we call deep time delay filter, as well as implement reinforcement learning methods for the CACC task. In this presentation, we will make use of this mind map to share with you our research results. let's return to the beginning, to the original sort of guiding questions that we formulated based on our review of the CACC literature. To address the lack of time varying delay considerations in literature, we wanted to answer one simple question. Is the popular use of epsilon max as the constant delay a safe approximation for any time varying delays? To find out, we chose to use the sinusoidal class of functions because they are bounded and they are periodic, and they also offer 4, not too many, not too few parameters to study. These parameters are going to be, for us, the upper bound A, amplitude B, frequency omega, phase shift C. Our first contribution was thus applying the semi-discretization method to find a numerically solvable condition for the CACC stability under the sinusoidal delays. Through some manipulation of our system equations, we were able to find a solution operator U and compute its spectrum to then conclude about stability. In simulation, we varied the 2 parameters at a time, and we found that frequency played a non-trivial role in the system stability for there's a certain range of frequency where the system will appear to have smaller stability margins. The effect of amplitude and phase shift, on the other hand, were less unexpected. By increasing the amplitude of a sinusoidal delay, the average delay is reduced, and thus, understandably, there is at a large enough amplitude, the system would turn stable. Phase shift, on the other hand, also did not have any really apparent effects on stability, and we think this might be because currently we consider all the communication links to have the same delay function. We also checked specifically for the difference between the constant delay approximation and the time varying delay, and despite both of these delay functions that we've tested to have an upper bound of 1 second, the stability regions are clearly different. Therefore, we conclude that in general, time varying delays cannot be approximated as a constant one using just its upper bound. Evidently, we found counterexamples of the sinusoidal time delay functions that made the CACC system unstable. We then turn our attention to large constant time delays. In literature, most studies use 100 to 300 millisecond time delays because these were the measured average latency of the IEEE 802 wireless communication standard. We want to know what would happen if we consider delays up to 1 second or even 5 seconds. In simulation, we ran many trials as a part of a sensitivity analysis, and we mapped out the stable and unstable regions as well as a counterplot of the rising time. We found for repeated values of time delays that lowering the control gain decreases the control performance, and the negative slope of the stability boundary forces us to choose smaller and smaller control delays as time delay increases. We call this observation the curse of the performance and stability trade-off because evidence show that for the OVM controller to stabilize larger delays, it would have to sacrifice control performance. This motivated us to look for new CACC control methods that can overcome this curse. Our first thought was to use a predictive approach, which we dubbed the deep time delay filter. Instead of redesigning a controller, we kept the conventional OVM controller, and then we implemented a filter module that can replace the delay compromised signals coming in with predictions of the up-to-date signal. If the prediction of these up-to-date signal is close enough to the actual up-to-date signal, then an aggressive set of control gains can be used to stabilize any delay, and we think that control performance should remain the same. We trained the DTDF models using an inner simulation loop that collected the training and validation data, and an outer supervised learning update loop that improved the model iteratively. This kind of training scheme was necessary because in practice, these predictions that the DTDFs were making relied on the previous time step, and it gets affected by the results will get affected by what it predicted in the previous step. So by using this scheme, this model should be able to learn and take this into the account. Making this training framework and optimizing it so that the inner simulation loop was fast enough during our experiments was actually a significant challenge to solve during this implementation stage. Here's the DTDF performance stabilizing a 5-second constant time delay, and we compared that to the OVM controller's best stable performance. The improvement that the DTDF makes is significant. Rising time and steady state error were both decreased, and the oscillation of the OVM controller is also mitigated. Our second approach was to directly replace the OVM controller with a reinforcement learning agent. Well, we were motivated by the numerous successful applications of RL to control tasks in the recent years. For the CACC community, several RL methods have been attempted, but the current state of art research is only limited to the car following behavior. The car following behavior here we mean is only 2 cars in the CACC platoon were considered. We also found one work that proposed a distributed RL agent for platoons with more than 2 cars. However, we ended up selecting the car following method as our reference because it was more cited. We felt limiting our work to just the car following task for now would give us a chance to answer our research questions without risking us to face many research questions or challenges that were still relatively unknown to literature. The RL agent directly replaces the OVM controller, as we have said, and in order to model the delays of the RL agent, we use a state that contains a history of actions. This is called the delay deterministic Markov decision process, and the extra history of actions allows the agent to predict for itself what the current state might be. Here's the result of the RL agent stabilizing a 200 milliseconds of time delay. There is significant improvement to the rising time, but the RL agent seems to have learned some sort of systematic bias, so it loses out on the steady state error. The bias is tough to spot in a real-time experiment, so we weren't able to catch it in time and attempt to correct it for the thesis. But moving the equilibrium target by 15 centimeters should be able to help us get a better steady state error. We will also note that for the 200 milliseconds here, we were limited by the convergence of the learning algorithm, and therefore we weren't able to train for any delays larger than 200 milliseconds. There's one last contribution that our thesis makes. All of the machine learning studies in the CACC space have shown results in simulations only. And so in order to shed light on practical considerations, the results for our DTDF and RL agents were all obtained in physical experiments. We've actually spent a considerable amount of time perfecting the physical test bed so that it can do this. Starting out with just an off-the-shelf real-time robotic platform, we found the need to add localization to help our robots drive in a straight line. Our second iteration used particle filtering because it was really cheap to do. No extra equipment was necessary except for some cardboard boxes, and it was relatively simple to implement. However, our trials revealed that the particle filtering was not particularly accurate or reliable, and setting up the physical environment was a tedious guesswork of which boxes should be placed where in order to get a good localization result. Most importantly, we had some suspicion that the limited sampling rate of the particle filtering, which was due to the Kinect sensor that were on board these robots, were causing problems in our experiments. Thus, in our third iteration at building the physical testbed, we added a camera system by OptiTrack that gave us 120 Hz of 3D position and rotation data at sub-centimeter accuracy. we also implemented a separate path following controller, which allowed us to get the robots to go to their initial positions automatically, and for the platoon to continue operating in much longer experiments. This is a video playback of the beginning of the DTDF experiments that we conducted. We tested the DTDF controller, the OVM controller, as well as a so-called PF extended controller, which stood for predecessor follower extended controller. And this latter most controller, we hoped, would functionally be the same as the DTDF without using machine learning. However, it just wasn't. You can see that both the PF extended and the CACC controller in the blue and red were oscillating, and they took much longer to catch up with the rest of the platoon. Here is the RL experiment. The best agent is in blue, and the OVM controller is in yellow. It has a noticeably longer rise time, while the other two agents were trained without time delay modeling, and thus it oscillates. So there are some, I guess, qualitative performance measures that don't seem to be captured in the plots, but when we look at the video playback, it is very obvious. In conclusion, our thesis uses the semi-discretization method to theoretically analyze sinusoidal time delays. We found that constant time delays don't always approximate time-varying delays very well. We also find evidence that CACC systems suffer a curse of performance and stability trade-off when dealing with increasingly larger time delays. And we therefore propose a new DTDF method as well as try implement RL agents to try and address this curse. We also experimentally we give experimental results comparing the performance of OVM, DTDF, and RL agents, and overall we found that both the RL agents and DTDF improved rise time significantly, and in some cases they improve steady state errors as well. There are three main focuses for our future work. One, we wish to conduct experiments with sinusoidal delays using the new testbed. And number two, DTDF and RL agents both provide good preliminary results, but they should be improved in terms of having better steady state errors, and we want to give more investigation into perhaps the use of better input signals or machine learning architectures. And finally, three, currently the DTDF and RL agent experiments only include one enhanced vehicles in the platoon at a time. It would be fruitful to experiment with multiple enhanced vehicles in the platoon simultaneously. This concludes our thesis presentation, and we'll now have the remainder of the time for questions. Thank you so much.
Thank you, Albert. Very good timing. I would propose that we start the questions and answers period from Professor York Lieberher.
Okay. Yes, thank you very much, Albert. This was a very good presentation. I also enjoyed reading your thesis. Now, you did a whole lot of work, and with my background, your thesis is a little bit of a waste, and my questions, sometimes you have to have some patience. They may come across as naive, but let me go through it. Kind of overall, kind of when you're describing your contribution, and in section one, in the talk you did, the presentation you did it, and in section 1.3, you described your contribution. But when I look at engineering work, there are, maybe I should look in this direction, because when I look at engineering work, there are typically two types of works. Is one of them you're doing something for the first time, and then you say so, then you claim the novelty, or you're improving something that already exists, and then you have to show the improvement. And in your work, I mean, I never found that you did something you never said that you did something for the first time. So what that, and correct me if I'm wrong with that. And kind of then with regards to, if that's correct, then I would know specifically from you what the improvements are.
Okay, yeah, I can answer that.
I mean, not a review of what you have, but
Yeah.
but just kind of with regard to literature. Yeah.
Mm-hmm. Yeah. So I think this is probably a blunder on my communication aspect, because we actually submitted a couple papers, and in those papers I was a little bit more forceful in my tone to deliver across like what we did that was completely new. So number one that was completely new was nobody in literature has yet described the CACC platoon with the sinusoidal time delays. And that was sort of one of our founding questions was we saw a lot of work that just says something like, oh yeah, because of the IEEE standard, it was, the wireless delays are maximum 300 milliseconds. So we use a maximum delay of, a constant delay of that 300 milliseconds and everything should be fine. And we just found that to be not very satisfying, because what would happen if the adversary, because our group is in cyber physical security, and so I'm very and actually at first I also had a course that was about adversarial machine learning, and so that caused me to really think about from the perspective of adversaries. And I'm thinking, well, what if I can design a delay that had a special frequency and it would cause instability instead of, in spite of you using the maximum upper bound to approximate your designs. And so this sinusoidal delays, we didn't find any work with regards to it. The closest that came to it was people talking about completely random delays. They would do it as a random process, and they would just say, okay, yeah, the random process is between a lower bound and an upper bound, and we do the analysis that way. So first of all is the sinusoidal time delay. Next one that nobody has done before is actually to consider the DTDF module. So that was something completely new, and we basically named it ourselves as well. The whole concept here was just to say that, okay, we've seen some really cool controllers in literature. The OVM controller as in particular is a very popular one, and we don't want to kind of just go out there and say that we can make better controllers. We just wanted to build off of an existing controller that was already good, so we didn't want to replace it completely. And what we did differently from other people, most other work would just say, okay, I want to propose a whole new different controller. We want to consider different parameters and things like that. What we did instead was we said, okay, in order to mitigate the time delays, let's add in a new block in front of the OVM controller that will hopefully make the performance better. And actually that brings us into the topic of something else that most of these literature don't do, is they don't talk about what the explicit performance of their controller is. They'll just say that yes, our controller is stable, but it doesn't actually talk about, okay, what's my rising time compared to other work's rising time? What's my steady state error in these scenarios? And our work actually is one of the in my opinion, one of the only ones that actually make this comparison viable and right there for people to see. And then finally, and I'll just be short on this one, is just we don't consider only simulations. All our work is in physical space. No other work really do this, especially with machine learning considered.
Okay, yeah. So you see that there's kind of in our world, there's a big difference between we are the only one who do this, or we are one of the only ones who do this.
I think,
and so these are fine. That appears like a fine point, but that's
I think it's
essence,
because,
and that's what I'm trying to understand. But you addressed a lot. Kind of in the in chapter. Let me see if I may have the chapter numbers wrong, but the deep learning part,
yes.
what you call the DTDF. you're saying you're working off this, you're improving reference one, and this reference one is the work on the OVM controller, or is that already deep learning approach there?
If you are talking about including reference one, I believe that one was the RL, and that one like is something that we actually only improved, and so I wouldn't call that like our biggest novelty. For the DTDF, however, like it wasn't improving, it was just completely nobody did this where we were the first, and I should apologize for
why not then
of,
state, I mean, that would be something that
okay.
in section 1.3 to just boldly state it. I mean, that's in particular if you have submitted papers. I mean, one thing I also should have said that at the very beginning, but I want to say it now. The work that you have done here is really impressive, and I believe a subset of that would be sufficient for any master's thesis. So I mean, there was the kind of the stability analysis with the control model, then the experimental work, which I assume was significant, and then the work on the Markov decision process with the reinforcement learning, and then with the deep neural network. That's, I mean, that's a lot of work, isn't it? Yeah.
It was a lot of fun too at the same time. But yes, I think the part is, as a young researcher, I'm sometimes not too sure where I should be bold and where I might just not have seen enough of the literature, even though in this work we've cited over 100 work, and we've obviously gone through a lot, and I really didn't see any. But I'm just worried that if I am so bold in making a statement like that, and then I just missed something out there. So I guess this is a place where I'm not too certain about, like, even if I don't see it, I don't want to say like we are the only one, but maybe that's my misunderstanding.
I'll think about it like writing a patent. So if you're writing a patent and say, this is a patent, I try to patent this, but I don't want to say I'm the inventor.
Right.
Then you don't get a patent. And likewise, it has to do with scholarly work. If you're coming out with a paper, trying to submit a paper, and you don't say this is novel or it improves something, then you get rejected. That's how these things work.
Right. Okay.
I see. So I mean, there's something in that this is also something where I completely may misunderstand the work that you have, but it's about the concept of delay that you have. So, I mean, these are really communication delays, end-to-end communication delays.
Yes.
And the sinusoidal pattern is, what is that? That is a delay that goes up, goes down, goes negative.
Oh, okay. So I guess that part I didn't get to specifically talk about is there are some assumptions on these delay functions. So if we just take a look at a constant delay, let's say we always have a constant delay of the 300 milliseconds, then I'm always looking at 300 milliseconds prior, right? And if I want to consider a time varying delay, then we sort of implicitly have a couple of assumptions about it. Like, for example, if it's going, like the delay function is going up, and it's coming back down, in that change, can it go, like the change, can it go greater than 1? Like the slope, can it be greater than 1? Because if it is
what
greater,
you're referring to, what you're referring to is delay variation.
Yes, yeah. So the variation, like,
that's not the same as delay. We kind of, and this is something I actually do know something about. So that's why my expertise is. Yeah. This is called the delay jitter. It's delay jitter. In communication networks, the delay jitter is the variation of the delay. Jitter has a different meaning also in another context, but with transmission of packets, delay jitter refers to the variation of the delay. But then if you have that, what is then the actual distribution of the delay? Because I this is something I've never seen a sinusoidal delay, and if you're looking, I look a lot at traffic. You don't experience that, but sinusoidal delay variation would be very regular, but
Yeah.
I mean, it's conceivable.
My thought when we conceived of the sinusoidal delay was really from an adversarial perspective. I'm just trying to think of what would happen if someone were to just generate a function, and a sine function is one of the easiest ones to generate for us, and then we just thought that okay, and then if we vary some parameters, we bound it by a certain value, would it become unstable? And
but by the same I just
that's okay.
By the same token, so if you're using that as an adversarial assumption, by the same token, this constant 100 millisecond delay that you say doesn't work so well is at some level also a worst case assumption. So it's also an adversarial assumption, isn't it?
Right. So I think that's why we were trying to show this. So let me refer also back to one of the photos here to help us. So this is what we found really interesting as a part of our research. Was everyone thinks that it is the worst case scenario, and here you can see in the figure A here, when you there is a certain frequency band that actually sort of causes your delays to become unstable. And yeah, that's what we found really interesting, because otherwise this bound here or the entire portion, as you vary omega, I should just expect everything to be stable, right? So that's where we found it was really interesting, and kind of shouting out to the community saying, hey, look at this, like maybe there is cause to study these delays, not at a worst case scenario, but more in depth, taking a look at what each specific parameters can do.
Yes, because in the end, that's possibly what you're pointing at. It is not the absolute value of the delay; it is the changes therein. Yeah, so in the distribution of the delay distribution. Yeah, so is that possible? Yeah, maybe something like that. Another question that I would like to ask about the delay. So, I mean, you get the 100 milliseconds from kind of the 802 specs as a requirement. Now, you move this up to 5 seconds.
Yes.
Now 5 seconds of delay is I mean, that is, I mean, look at the delay that we have right now. It's in the order of less than 100 millisecond. Yeah, did you see it? 5 seconds, we would not be able to talk interactively. Actually, starting at somewhere 150, 200 milliseconds, we would no longer talk interactively. We would just finish speaking and then point. So you're going into the 5 seconds, and I don't understand why you have those large values. On the other hand, there is this technology trend of using 5G cellular, and that has a service which it's not in the current deployment of 5G, but it's something that will eventually, it's part of the specification. It has this ultra low latency loss service which promises a latency of less than a millisecond. Yeah, so I mean, why do you go in this? I mean, what makes you go into this direction of these super long delays?
Right. And
I mean, you're preventing collisions. Sorry, you're trying to prevent collisions, and 5 seconds. That's Go ahead.
Right. So I think again, looking back at sort of where we got motivated from the cybersecurity sort of perspective, if we have an adversary and they were thinking about how best to sort of wreck your platoon, and then they go, okay, well, the norm is 300 milliseconds, and I'm wanting to wreck this platoon. So what do I do? The easiest thing they can do is just ramp up the delay value, and I think there's not really a upper limit to how much they want to deteriorate your values by. And you can argue that even if they are very obvious in their attack, that you can just mitigate it by switching to a different mode, switching to a different communication channel, and things like that. But let's pretend that there wasn't a different communication channel for you to switch to. Then for us, you just have to switch to a different controller, or to just adjust your controller so that it can somehow mitigate the delay. But then, as we show with the cursive performance and stability trade-offs, if you do that, you're essentially telling you're essentially saying to the adversary that I lose, and I'm going to take some cut on my performance to stabilize your delay, right? And if we are able to then consider much higher delays, so that even if it were very, very high, we can still have the same kind of performance. That's what we were after, because we just don't think that we just don't think that it is necessarily impossible for an attacker to consider 1 second delay, 5-second delay. I mean, if I were trying to attack a network, that's probably one of the first things I would do.
So what you're stating is that you provide stability for any delay following a sinusoidal sinusoidal change of the delay with an upper bound of 5 seconds, that you can provide stability. I mean,
right.
I mean, is 5? I mean, if we had in 5 seconds, if you have that, even if you can get stability, is the application still viable? If we had in this Zoom call a delay of 5 seconds, the application would no longer be viable. We would not be able to use it. We would use the telephone or use email. Yeah, it does not work. If you're thinking about this application on a highway where cars are moving at 50 kilometers, 100 kilometers per hour, 5 seconds is can you? I mean, if
it's kind of bizarre. Like how is it doing it? Kind of is that where you're trying to drive the question?
I don't want to say bizarre, but what is it that you have in mind? I mean, is it still viable? Yeah, for the application.
Right. I really think it is, because the 5 seconds delay is just what an adversary will do. Like, that's just what they can do. I won't say will. I shouldn't say will. I should say that they can do this. And when they give us that 5 seconds delay, then we just have to do something about it, right? And the DTDF module was designed to do that. Was designed to say, okay, well, you have 5 seconds delay. I have my advantages as a CACC platoon, because I not only get the information from the previous car, I also get it from the leader car. I also get it from any car in front of me. I can grab that information. So why don't I use that to my advantage and try to sort of, well, I guess in this sense, do some magic with it, and then be able to still control myself, despite you giving me a signal from 5 seconds ago. So, yeah, I think the feasibility part here is not really from the perspective of, is the application still viable? I guess that is the thing that we're trying to do, is to make it viable.
Okay. Fair enough. Thank you. Let's see. Okay, I have to say one thing. So I just received your thesis just 1 week ago. Yeah, so I was added late to the committee, so I didn't have a chance to read all of the thesis in great detail, but I read all of the thesis at some level and some of it in detail. There are many grammatical mistakes in your thesis, and this is in the order of, I cannot say for sure because I didn't mark up the entire thesis. I would estimate in the order of 100.
Oh, okay.
There are, and they're very benign, but always the same type of error
Mm-hmm.
with singular, plural on the verbs,
Mm-hmm.
and uh, articles, kind of this N versus A, yeah,
Oh,
N
okay.
traffic
Yep.
manager. This images illustrates, yeah, so this singular plural, there are many of those. And there are also quite a few. I don't know how many. I saw maybe three, four uh, um, references that were not compiled. So
Oh,
undefined references in LaTeX, which when you compile it gives you a warning, yeah, so that there are undefined references or some references not found. That's the question. There are quite a few in there.
oh, interesting. Okay.
Um, it's the version that I have, which I received. And thanks for the attachment of 70 megabytes. That broke a record. Uh, good. So yeah, so yeah, sometimes yeah. So that's a remaining issue in your thesis.
Okay. Okay. Yeah, I try to
Uh,
use Grammarly. Grammar is not my strong suit, but thank you so much for catching those, and I will take a look at that.
good. All right. With that, I would like to pass on.
Thank you, Professor John Simpson.
Hi, can you hear me okay?
Yes.
Okay, great. Um, okay, so um, thanks for the presentation. Uh, yeah, I guess I'll echo the previous comment that, the work here is pretty expansive in terms of its scope. I do want to drill down on some of the details because I felt in particular in chapter 3. A lot of this thesis is ostensibly focused on control, but I felt like um, the the explanation was sort of weak, and I couldn't really follow
Okay.
a lot of what you were trying to do. So maybe first I'll start with the sinusoidal delays, since you've got that slide up already.
Okay.
Um, so I couldn't quite parse the motivation for this sinusoidal delay pattern.
Mm-hmm.
So I've heard you say sort of two different motivations, perhaps. So one motivation is, well, we're interested in potentially time-varying delays, and this is a time-varying delay, therefore it is of interest. Um, which, okay, it's an example of a time-varying delay. And the second possible motivation you said was, okay, we might be interested in adversarial delays if somebody is mucking around with the
Mm-hmm.
communication. I don't quite see how this could model an adversarial delay. I think that's a totally different problem setup. But can you speak to this? So
Yeah.
what's the practical perspective on this sinusoidal delay?
Right. Okay. So maybe I am naive in sometimes my considerations about what an adversarial will do, but when I took a look at it, the reason I considered a sinusoidal delay was just simply, um, if I am trying to attack this platoon, what is available on hand that isn't really considered by literature right now? And the literature talks about constant time delays. Well, what about a sinusoidal one? So I think in essence the motivation of using this is really, really simple, and nobody studied it. That's why we're doing it. There's really not nothing, I guess, special about the sinusoidal delay. There is 4 parameters that we really love to be able to tune, like we can build in that upper bound, we can talk about the amplitude, we can talk about the frequency and phase, and sort of to dive in a little bit deeper into why these particular parameters were interesting. Actually, it was the frequency and the phase that got me, because I'm thinking, what if in a heterogeneous platoon setup where all my delays were different, what if I use some sort of phase shifting? Would that somehow amplify the disturbances and the errors that were inside the system? That was sort of my thought, because I'm going, when we were doing just some preliminary sort of experiments, we kind of discovered that, okay, if there is one particular vehicle link that has a strong signal, and maybe strong is not the best word, a good signal, and whatever that definition of good we haven't really defined, but in my sort of very naive sense of what good is just that it's not as delayed. Okay, so if there is just one link that was relatively good, then we found that, hey, the platoon was able to at least stabilize itself pretty well. Now, what would happen then if I sort of just offset all of my all of my delay signals coming in so that there were no good signals at all? Never. But then when you look at each particular delay function, like if I have an algorithm that just identify the delay function and go, hey, is this delay function something that I should be worried about? And they say, well, just by looking at itself, it's fine. I can stabilize this. But when I put them all together and I shift them around so that the phase, make sure that nothing is synchronized, everything is always bad, then maybe I have a case for instability. We weren't able to get to that in this thesis because we consider only homogeneous delays, which unfortunate. But then the other one is frequency, which we're interested to find that actually there was a particular band of frequency that caused something that was non-trivial in the stability region.
Sure, I understand all that.
Mm-hmm.
I think the scope of what you can learn by studying this sinusoidal delay
Mm-hmm.
Seems very narrow to me.
Mm.
It seems that I don't see how the conclusions could be extended to any other like functional form. It's not clear like a functional form like this would even be an appropriate model of
Mm-hmm.
the kinds of delays that one would expect from the communication technologies.
Okay.
To me that would have seemed like a more natural
Right.
Way to proceed is what's the communication technology? Can we somehow come up with a model, perhaps an approximate model of what the delays would look like coming out of that technology,
Right.
and then study that form of time variation?
Right. I think the current literature does quite well in doing that already, and I think at a certain iteration in my work, I call it the natural time delays, which is what would naturally come out of the wireless communications. And I think actually when I read the literature, they consider random processes, and I don't disagree. Wireless time delays are random processes, and I don't see any reasons to call that a limitation. However, when I consider what would happen if we don't have natural time delays, and because again our group's focus was in the cyber physical security systems, so I'm very sort of biased towards thinking about, well, what could happen rather than what does happen all the time. And so adversaries don't have to follow just giving you random time delays. And as well, I also have a sort of a thought about why I chose sinusoidal delays, was just thinking about, being able to mix them together. Like, what would happen if I now put two sinusoidal functions together to make a different function? Maybe then studying the sinusoidal functions has merit because it provides a foundation for, the whole family of functions that can arise from it.
Well, perhaps it's not clear if it actually does that or not.
Right. Yes.
In any case, I found the motivation for this functional form a little bit lacking.
Okay.
And drilling down now to some of the technical details.
Yeah.
So I could not understand the sort of mathematics that preceded this stability region analysis here.
Okay.
So there was some description of this. There's a matrix X, like maybe on the previous slide. At the bottom equation here, I think was sort of one of the key ones. Just from the description in the in the write-up, I couldn't follow what was happening. So
Right.
do you want to maybe take a 1-minute shot at explaining
Sure.
it again?
Sure. Yeah. So, you're talking about this x of t here. This was sort of the target equation that we wanted to get arrive to, and this was kind of in the Foucault theory. We were just thinking that, hey, things were periodic, we might be able to apply this, and so that's what we tried. And the rest of it, the semi-discretization portion, was really because, well, inside our time delays, we can't really have something that was finite. It wasn't finite dimensions, so we had to just break it up into different chunks, like to do an approximation, so that we have then a finite dimensioned matrix, which then was the phi matrix that we ended up constructing. I do have some backup slides over here we can dive into much deeper, but I'm just going to hand the mic back to you for now.
Sure. I think the starting point, like the infinite dimensional setup, was unclear to me.
Right.
So I think, maybe just the writing there could have been refined to sort of ease the reader into that a bit. The question I had about this discretization was there was some parameter, I think K, you called it, that needs to be chosen as part of this discretization. From the reading I did, I guess K needs to be large, but I didn't see any sensitivity analysis in your thesis about this approximation error, and like what are the guarantees that you get after you do this approximation? What can you actually conclude about the original system?
Right. This part, yes, we didn't do the sensitivity analysis portion, so I think more work would have to be done there, and we would probably have to just observe that as a limitation to the work that we've provided so far.
So those plots you were showing, for instance, of B omega, that plot?
Yeah, let me just get back to it. This one here.
So, yeah, that one. So these plots were computed using this approximation, right?
Yes, that's right.
So did you ever validate these plots against a time domain simulation?
Yes, we did. Yes.
Okay, so you actually verified that, if I picked a point maybe like in that white region, in that hole in the middle, then actually the platoon's unstable if you run the time domain simulation.
Yes, indeed. So we made these plot two different ways. So I had two different kind of simulation. This one was done in Julia, and because they had the discretization package and whatnot, and then the other one we did in MATLAB, which we used the DDESD solver, and that one solved the time delayed systems, and then we would do that for a whole bunch of different points. So we would go across this basically use this as the parameter space and just choose coordinates on it, and then run it, and then we had just a quick sort of measurement about like a set of heuristics to say whether or not it's stable or not, and then we plot it and get the same looking plot. Yeah.
Okay. Good. So my next question, was about the constant delays.
Okay.
So, I think I agree with a lot of Jörg's comments about the size of these delays. I think if I ping my computer to Auckland, New Zealand, I maybe have 300 milliseconds.
Right.
So the practical relevance of a 5-second delay or something, I think it's a little bit hard to make that case. I've heard you try to make it, so we don't need to go down that road again.
Okay.
But yeah, I'm not sure I buy the adversarial angle there particularly. Okay. The next part, or the last part of the thesis, I guess I'll comment on because it's sort of in my area of expertise, is chapter 6. So this this method you came up with for what I can gather is essentially delay compensation. So this is the
DTDF.
DTDF, right?
Yes.
Um, so my reading of this was you're using you're using a learning-based method to predict what the states would be if you didn't have the delay.
That's right.
Is that
right.
the gist of it?
Yeah.
So yeah, I mean, in control, like this would be referred to as a delay compensation method. It's a heavily studied area. There are techniques dating back to the 1950s that effectively do this.
Mm-hmm.
Yeah, it felt odd to me in this section that, I realize it's the style of the time. You jump to a deep learning based solution,
mm-hmm.
but to me it felt potentially like overkill, given that there are very well established classical methods for compensating for delays, and it was unclear why those were not an appropriate solution here.
Okay, yeah. I am I'm a pretty new researcher, and I think actually there are some keywords that when I search for, like I would search for something like delay predictions and things like that, but I didn't know of certain keywords like delay compensation. So there are probably some literature that didn't crop up in my research. The thought here was just simply instead of maybe I went and reinvented the wheel, which is totally possible, and then I used a deep learning method, which was overkill because there was already well-established control methods that do so. But unfortunately, this was just perhaps something that we couldn't have seen at the time of working on this.
Fair enough. So some of the classical methods would be the Smith predictor, possibly the oldest method for delay compensation.
Mm-hmm.
Another simple method is in a discrete time system, you just augment additional states which store the old values of the variables, and that can help you compensate for delays. And then there's a whole subfield of control concerned with designing controllers for time delay systems, or otherwise augmenting existing controllers to ameliorate the effects of delays. So I mean, from a control perspective, this whole section felt a little funny to me.
Thank you for the suggestions.
I think that's the majority of my comments. So I guess to summarize, maybe I think the breadth of the work here is very interesting. Going from a little bit of theoretical analysis even all the way to some good experimental implementations. But I think there was a lot of depth that was sacrificed in order to do that breadth.
Right. Yes.
And for me, that stood out in the thesis.
Okay. Thank you.
Professor Mohammed El Junaido.
Okay, thank you. So, Albert, actually, I have a couple of questions regarding the delay. Now, from the literature review that you did, we figure out that there is a trend when we do control for connected autonomous vehicles that a number of studies, recent studies, they start to claim that we have time varying delay or time varying delay that is bounded by a constant. And then they do some uncertainties, boundedness analysis, and then they design nonlinear control system. And this is only based on assumption that the time varying delay is bounded, right?
Mm-hmm.
So what do you conclude when we consider slight uncertainties by considering delay with some errors within this delay when they consider it, right? When for example, when you have a model for the connected autonomous vehicles, and instead of considering tau, you consider some uncertainties in this tau, and this is what we call here time varying delay. So what was conclusion for such functions?
You're talking about like those studies that perhaps consider constant delays, and then they have some sort of I guess uncertainties on that constant delay. So then so most of those ones, that actually all of them that I've seen, they consider just they consider the errors on that to just be random as well. So essentially you can classify it as another, like it's just exactly the same as a random time varying delay, with an upper bound that is, I don't know, c above tau, and c below tau, and that's just the two new bounds, and then the analysis would be the same as before when they consider just time varying delays. So
yeah, exactly. So like when you consider the proposed function for the time delay, like you would like to propose that, okay, if we have increasing or decreasing in this value of the delay, so to consider some uncertainties, and this is for the delay is a very sensitive issue from stability point of view, because once you start to have like a delay and you are adding like a time varying within this delay, you will have infinite eigenvalues, right? So you are getting into a totally different domain, just because you are adding some uncertainties for this function, right?
Right.
Okay, so my second comment is about the semi-discretization method, which is a common method for time delays, right?
Yes.
So, like, what do you conclude about the eigenvalues that we have from semi-discretization methods that you consider for the time delay?
Right. So once we did the semi-discretization step, which put us into a finite dimension, we were then able to look at the spectrum, and then if they were all on the left half plane of the complex plane, then we were able to conclude that the system was going to be stable. And
exactly. So yes.
Yeah. But because this is finite now, but when it was infinite, then we can't really conclude that.
Exactly. So like we use this method in order to obtain stability,
yes,
that you show all the eigenvalues. With this numerical method shows that we have negative eigenvalues, and then the system will be stable under the time varying method. And this is the main advantage of having like semi-discretization method.
To have this stability. And unfortunately I didn't write that. I didn't even put that in the presentation, but thank you so much for bringing it out. Yes.
And the third issue is the large delay. Now, as you figure it out, that they start now to use the connected autonomous vehicles in order to control the flow, the what they call the waves, stop and go waves, right? In the highway.
Yeah.
Right. And now they start to suggest that they can use the autonomous vehicles in order to control the traffic, right? To wave. To, if we can say, reduce the jump within these waves, right?
Yes.
Within like a stop and go wave, as you start with the thesis.
Right.
And when they do this analysis, they completely ignore any human factors within the human-driven vehicles, right? And they ignore any kinematical issue when we have like communication between autonomous vehicles and the human-driven vehicles. And we know like human factors, when they're considered within the network of autonomous vehicles, and instead of having like a delay of 100 milliseconds, you can come up with like 2 or 3 seconds time delay, right?
Oh,
so like when you consider the high value within the time delay, you are considering the human-driven vehicles within the connected autonomous vehicles, which will like increase the value of the delay that we have here. And this, like from the analysis that you did, you showed that considering such a delay to control the traffic, and without considering the time delay, we may have unstable issue within these challenges, right? Within the connected autonomous vehicles.
Right.
Like they completely ignore that we have a human-driven vehicle between these autonomous vehicles, right?
Yes, because the proliferation of autonomous vehicles won't happen overnight. They won't go from 0 to 100. So there's going to be some human-driven vehicles still on the road, and we have to consider them and model them, and that's another place where the high constant delays can arise.
Yes, exactly.
Yes.
Okay, thank you.
Thank you.
Thank you. Professor Deepakunda?
No, I'm fine, thank you.
Okay. Any further questions from our committee members?
Yeah, I could briefly ask a
Sure.
question, just out of interest. So when you kind of in the later parts where you use the machine learning methods, in particular the deep learning, the computation itself, I mean, does that become an issue?
Right. It actually
in your system?
It does for our physical setup, and actually in I think it was it chapter 4, we go in depth into some of the drawbacks of choosing the Quanser Qbots instead of some of the other ones that use the Jetson Nano chip, because they have on the Jetson Nano they have GPUs in it, and the Quanser Qbots don't.
They have Raspberry Pi 3s,
Yeah,
is that right?
yes, that's right. That's not
very
gonna run it. So we actually spent a long time trying to get it to work on the Raspberry Pis. Our networks are relatively simple, just like fully connected perceptrons, sorry, not perceptrons, just fully connected deep networks, and we thought these were gonna be able to run on the Raspberry Pis, but there were actually another layer of difficulty that we met during the implementation, which was just that we simply couldn't make them code generated into the C code that the Raspberry Pi then would take to run. And so our solution with that, which is currently, I suppose you can think of it as a limitation to our work, is we had to run the inferences on the host computer, and then the host computer would then disseminate the information to the robots.
But in real time?
Yes, well...
In real time. Well, I mean, that's like the same. Yeah. I mean, I don't think that's an issue. I mean, you see a lot of that in edge computing.
Right.
That edge devices upload material to the cloud.
The thing is, it wouldn't really be edge computing anymore, as far as I am read up on. Like the edge computing is where you actually want it to execute on board, and then our model is more close to the cloud computing, where the cloud does the compute and then it is sent to the edge for further process or whatever.
That's fine.
So I guess it is fine. It is fine. I personally would have wanted to drive for the machine learning to be on board the Raspberry Pi, but unfortunately it's just something we can't do right now.
Yeah, but if you have these NVIDIA processors in there, I mean, then I mean that would probably work out fine. Yeah,
yes.
Because power is not an issue in
that processor. Yeah.
The other question I want to ask, just more informational. You mentioned that you have a couple of several submissions or even publications. Can you speak a little bit to that and just say where you submitted and maybe show the first page?
Yeah. So I don't know. I have a slide here. Just listing them. We got one accepted. This one was particularly about the analytical portion, so the semi-discretization with the time varying delays. It was accepted in the IROS one. We made a journal version of it to go to the TCST, and then for the deep time
TCST, transaction on I'm sorry, I'm this is not my field. So
sorry, actually I'm gonna have to look up that abbreviation as well.
It's the control systems technology.
Control system technology, thank you. And then for the deep time delay filter one, so the deep machine learning stuff, at that time we didn't have the RL, the reinforcement learnings, so we only had the deep time delay filter. We submitted that to the ICRA and also the TCPS, and those are still under review, unfortunately. So
but that's outstanding. Congratulations.
Thank you so much.
That's all I have. Sorry.
Right. Any other questions from our members of the committee? All right. So if not, I would like to ask our guests, our students in the audience, to leave the virtual room. And Albert, I might need to somehow put you in the waiting room or something.
Okay, yeah, so I can leave the meeting and then rejoin and just be in the waiting room?
I can put, if you can't, I can make you a co-host, Bao-Chan,
Or you could just add.
I can do it myself. It looks like I can put people in the waiting room. So
Okay.
Albert, I will put you in. Okay, let me try to figure out. Okay, participants. Okay, I could do it before. What happened? I must have been looking in the wrong place. Let me see. Okay, I'll withdraw you as a co-host. Now I can now put you in a waiting room. Okay, I
Okay.
have to withdraw you as a co-host. Okay.
Okay.
With all of the work that you did, fabulous work. Do you want to take a photo
Oh yeah,
with
sure.
everybody, like a screenshot?
Okay.
You're muted.
Oh, I'm muted. Hi, thank you so much. And yeah, it was a really good time presenting to all of you, and thanks for the questions. I have snipping tool here. I can take a screenshot, or is there a better way?
No, that's the only way. No better way.
I can do it for us if you like. I'm on a
Sure.
Mac. It's very convenient, right?
Oh, okay.
Okay, so let me do it. So I'll do, okay, so on the count, you can all hear me, right? On the count of 3. Okay, 1, 2, 3. Okay, I can do another one. Okay, great. I'll send those to everybody, including you, Albert.
Okay, thank you.
Thanks, Deepa.
All right, thank you.
Okay, great. Thank you. So there's a few things that have to happen immediately. I'm going to send a message to SGS and NADA that your thesis is ready for submission. Bao-Chun will do his part, and have a great celebration tonight.
Thank you so much. Thank
Okay.
you.
Albert, we'll be in contact. I know we need to bring the test bed back, and we'll be in
Yes.
contact about that, right?
Yes, we will. Okay.
Yeah. Okay. Thank you.
Thank you, everyone.
Thank you, everybody. John, thank you. Jorg, thank you for last minute. Thank you. Okay. Bao-Chun, I really appreciate you being the chair.
No problem.
Okay. And Mohammed, you did this was mostly you. So congrats.
Thank you.
Okay. Okay. Great. Okay.
Right.
Bye, everybody.
Have a good weekend.
everyone.
Hi, Albert.
Bye.
Congratulations again. Bye.